Welcome to Lecture 13, entitled Strategies for Choosing New Variables, Double Integral. The material for this lecture comes from section 16.7 of the textbook, and the objectives are to develop techniques for choosing the functional relationship between the original variables and the transform variables for double integrals. Concepts and visualization skills. These are basically cases that can arise where you're given the change of variables, and you're just supposed to implement things. The other is a change of variables, which is determined by the 2D region. And lastly, change of variables determined by the nature of the integrand. As usual, the second slide is just a summary of the slides to follow, and so we'll just skip over this. All right, so this is a summary of the various strategies that can be used to choose new variables. Well, the goal of changing variables is to evaluate an integral in the xy plane in a transformed plane, which we'll call the UV plane, where the integral and or its bounds are simpler. I mean, that's really what we're trying to do, is to make life easier for ourselves. And so here are some of the four sort of what I would call general rules. First is aim for simple regions of integration in the UV plane. Secondly, ensure that the transformation and the inverse transformation are easy to determine. So if you know x is a function of u and v and y is a function of u and v, then the Jacobian is easy to compute. If you know u equals capital G function of xy and v capital H function of xy, then the boundary to the domain S is easy to sketch and to determine. So in principle, you need both of them to be able to solve a problem. That is to basically do an integration using transform variables. So third thing is to choose new variables based on the integrand. That's another option. And so I give you two examples here in terms of how this could be done. Option one is to consider an integrand expression that's shown, which is the square root of x minus y divided by x plus y. And what we do here is to define two different expressions by two different variables. So for example, u basically can represent x minus y, which is the numerator term, and v can represent x plus y, which is the denominator term. So this is just an example how things could be done. It doesn't necessarily have to be done this way, but it seems logical to try that because the final expression looks a lot easier, for the integrand at least. Second option, an example, is to consider the following integrand expression, x plus 4y to the power 3 halves. So what we could do in this case is define one expression by a variable and equate one of the original variables with the new variable. So for example, we could say u is equal to x plus 4y, but we'll let v equal y. Again, this is just a choice. It may work out, it may not, but these are sort of examples as to how to approach a problem. And the fourth thing is to choose new variables based on the region of integration. For example, if the region is bounded by pairs of parallel curves, then assign a variable to the pair of curves that only differ by a constant. We actually did such an example for the 3D case at the end of Lecture 12b, and I alluded to the fact that we'll be discussing techniques in this lecture, that is Lecture 13. All right, so let's go through the various cases. Take an example illustrating a double integral with the change of variables given. And so the objective is to evaluate the integral over region, integrand being square root of 2x times y minus 2x. R is the parallelogram in the xy plane with vertices 0, 0, 0, 1, 2, 4, and 5, 5. And that's basically what you see over here, the picture on your left. So there are your four vertices, and this is what the object looks like. Now, we look at this one, you'll notice that the lines, the edges are all straight. And so it would make sense in a case like that to use a linear transformation. And the idea would be to try to get that such that it forms a square, because then we know the integration bounds in the transform system are much, much simpler. And so the suggestion here is to use a transformation x equals 2u and y equals 4u plus v. All right, this is a suggestion. Idea being that we can transform this, which is sort of a difficult object to integrate with, to something as simple as this, where we just have straight edges parallel to the axes. So with this transformation, we can then start to move ahead And so what we need to do is map the points on the boundary of the original domain R to points on the boundary of domain S using the inverse transformation. Recall, we need both the transformation T and the inverse transformation T. The inverse transformation T will allow us to basically map points in the XY domain to points in the UV domain. So here's basically our transformation that we started with, put in matrix form. So this the set of equations in matrix form would look like this. But I want now u and v as a function of x and y. So I just multiply both sides by the inverse of this matrix, which is what you see here. And if you do that, you end up with this matrix shown here. If you write this out in equation form, this would be 1/2 x equals u, and minus 2x plus y is equal to v. And that's basically what I've written here. So this is the inverse matrix, and this is the original matrix. And they're linear. You'll see they're linear in the variables y and x. X, in this case, x is linear in u and v. If you have a transformation which is linear, then effectively all you need to do is to do the mapping of the vertex points. Vertex points being this one, this one, this one, and this one. And so that's basically what's being done here. You take x and y, which are 0 and 0, right? You plug them into here, and you basically determine what the new vertex points in the UV plane are. And you do it then for 0, 1, then you do it for 2, 5, and 2, 4. So effectively what we're doing is we're just establishing the point, this point, this point, and this point, 4 points. And the red line then corresponds to this line. The blue line that you see here corresponds to this one. The line that goes here corresponds to this one, and the line that you see here corresponds to this one. So now basically we have the boundary base in the VU domain. So that part is basically finished, and we can actually write down what that boundary ought to look like. This will actually become the bounds on the double integral, one for u and one for v. All right, so the integrand now basically gets replaced. So we know what the transformation for x and y is. You make the substitution, and you end up with the square root of 4 uv. We need to also compute the Jacobian. Normally we would take the absolute value, but if you basically started with a set of equations which are a right-handed coordinate system, then the value will be positive. In this case, it turns out to be the case. So the Jacobian is just take x, derivative with partial with respect to u, partial with respect to v, which would be the first row of the matrix, and the second would be dy du, dy dv partial. And then you take the determinant of this matrix. So after basically calculating these derivatives, inserting, we end up with this. And now we take the determinant of this, would be 2 times 1 minus 0, which is 2. All right, so now that we have the determinant, we also have the bounds. We basically just make the substitutions. So this becomes 4 root uv, which is from here. This du dv, this becomes 2. And the integration bounds are 0 to 1 and 0 to 1. So this is for u, and this is for v. This is from the previous page. Integrate with respect to u, holding v fixed. All right, and then integrating v then, between the upper and lower limits, and you end up with an answer of 16/9. If you look at this in terms of picture form, this is what we had started with in terms of the integrand, and this is what we're looking at basically after the transformation is applied. So this would be uv, it's w, and this is the shape of the object. And so we've gone from this to this just in doing a transformation from x to y to u and v. And clearly, yeah, this will look different. It'll still be in this direction, but it'll have a different form to it. All right, now let's consider change of variables determined by the region for the double integral. And so what I show here are two specific examples. If you look here, you'll see a straight line and a straight line. And so the only difference between these two is that this is being offset by a certain amount. So if you were to add a component in this direction, then you could get these two to match. Similarly here, if you add an offset to that, you can get these two to match. You can also have curved lines, such as this and this. Again, these are basically identical except shifted by a constant value, and similarly these two. Again, in a 2D setting, regions are bounded by contours. And so these 4 lines basically internally describe the region of interest. And so this is one example. This is a second example. And this will be the transformation that we'll be applying. And so what we really would like to do is to take this region, right, and transform it into something that would look like this. And we could take something like this and transform it into something like this. Right, so that's basically what we'd be trying to do, because once we have something like this is a simple integration because the bounds on the integral are just constant values. The constant values for upper bound v, lower bound v, upper bound u, lower bound u. So this is basically what we're dealing with. And again, the ordering of these is important when you're doing integration, which is the upper one, which is the lower one. All right, so let's basically go through the example. This is the case where we're dealing with curved lines. And so in this example, we'll let R be the region in the first quadrant. That means positive y, positive x, bounded by the parabolas x equals y squared minus 4, x equals 9 minus y squared, and x equals 16 minus y squared. The objective is to evaluate the integral y squared dA. All right, so we can basically look at this type of expression, and we can rewrite these equations in a form where it becomes immediately obvious as to how to select new variables. So for instance, we could take these bounding surfaces and just get all the expressions onto one side, leaving 0 on the other side. So for instance, the first two, you'd end up with x minus y squared equals 0 and x minus y squared equals minus 4. For the second two, you have x plus y squared equals 9 and x plus y squared equals 16. But you'll notice this and this are identical to each other. And they're equal to constant values, so this constant value is offset by this constant value by minus 4. Similarly here. Of course, these two are different, so why not just call this a new variable? Let's call it u. So this becomes u equals 0, u equals minus 4, and call this v equals 9, and v equals 16. Right, so that effectively now sets up our boundaries. We've got simple boundaries to deal with. And those boundaries you can see right here, because we've chosen v equals 16, v equals 9, and we've chosen u equals 0 and u equals minus 4. So this would be the region that we're going to be transforming to. Right? And so this is basically going to be t inverse, because in this case it's u and v as a function of x and y. And we can immediately write down what the domain would look like. All right, so the next thing would be, well, we're going to need the Jacobian, so we need t. We have t inverse, but we'll need t, so we need to basically write these expressions in terms of x and y as a function of u and v. So that's the next step. All right, since we need to compute the Jacobian, basically when you take the inverse, you'll end up with x equals u plus v divided by 2, and you'll end up with y is equal to square root v minus u over 2. If you want some more detail, just look down here. You'll see, for instance, what I've done is I've taken the original expressions that we had, u and v in terms of x and y, and I've written it in matrix equation form. So u would be x minus y squared, v would be equal to x plus y squared. And so what I want is, instead of u and v as a function of x and y, I want it the other way around. So we can take this set of expressions and multiply left and right by the inverse of this matrix, which is here. If I compute the inverse of the matrix, I'll end up with this value here, which is 1/2 this uv. Okay? So, but that would be xy squared. Well, that's okay, because if I want y, I just take the square root of the final expression that I get. So I can write these out as basically an equation in terms of u and v, and I can write y squared in terms of an equation in u and v. So note, the positive square root was chosen. Okay, you might ask, why not plus or minus? Well, it's chosen because y was in the first quadrant. So this is the only choice. This is the obvious choice. Okay, so now we have to also check that the points of S satisfy the condition that v be greater than u. Why? We don't want this to be an imaginary number. And it turns out, yes, it is defined. So essentially everything basically is okay. We can proceed. So now we compute the determinant of the Jacobian matrix, which is take the derivative of this with respect to u, with respect to v, first row, derivative with respect to u, respect to v, second row, compute the determinant, all right, and you'll end up with this expression here. We now just have to transform the integrand, so y squared now in terms of v and u will just end up being this expression. We get that by just squaring this, and that just becomes v minus u over 2. All right, so the rest is mechanics now. So there's y squared dA, that's what we started with. The bounds we already said were -4 to 0 for u, 9 to 16 for v. This is a substituted value for y squared. We computed the determinant of the Jacobian matrix, which was this term that you see here. And so now everything is in terms of u and v, and this integral is much easier to deal with. So first you integrate with respect to u, which means you hold v constant, and then finally you integrate with respect to v. So these are just the different steps along the way until you end up with a final answer of 18.79. Okay, so another example illustrating change of variables, but determined by the integrand for the double integral. All right, so in this case, we're basically given a square with vertices 0, 0, 1, minus 1, 2, 0, and 1, 1. So the boundaries are linear. I mean, they're straight lines. And so this, we could integrate this if we want to do, but we would have to do it in two regions. One would be with a line to the left, and the other one would be this with a line to the right. So it could be done, but it's just an extra step. So what we're going to basically do is to come up with a transformation. And the simplest thing would be if we could somehow figure out how to rotate this, because if we rotate it, we have straight edges, and this is a simple integral. So again, just to remind you, transformation t, which is x as a function u of v and y as a function u, is required to determine the Jacobian, and t inverse, which is u equals function capital Gxy and v equals capital H function hxy, it's required to determine the integration bounds. Okay, so compute the integral in the transsystem form equations. We're going to let u equal x minus y, and we're going to let v equals x plus y. And what does that transformation actually do? It just takes this object and it rotates it, but it also basically applies a magnification factor to it. So for instance, you'll notice that the lengths of these sides relative to the length of these sides are not the same. So it looks like we've basically expanded the size of the object. All right, so if you basically make this selection for u equals x minus y and v equals x plus y, which is what's going to go into here, we also would need the inverse, that we need x as a function uv and y as a function uv. If you do that, just a linear equation, then we end up with this for x and we end up with this for y. Okay, so we more or less basically now have everything that we need, and the only thing would be, for instance, the transformation of the vertex points in the xy domain to the vertex points in the uv domain. And that's simple to do because we have the transformation here. We have the inverse transformation here. So you just take your vertex points, right? And you can compute what the vertex points for uv would be. And so you just step through each one of them. So from here to there, to there, to there, and back. So this line basically is transformed into this line in uv space, this line to this line, this line to this line, and finally this line to that line. All right, so now that we have everything, we just make the substitutions for x minus y and x plus y, and you end up with this for the integrand term. This basically is just going to be equal to 1/2. You can do the computation, just take the Jacobian. I didn't bother to do it here. duv, and the bounds basically we've computed, which will be 0 to 2 and 0 to 2, which you see here. And so the next thing then is to integrate with respect to u, holding v constant, and finally integrating with respect to v, and we end up with this being the final answer. All right, that concludes lecture 13. Thank you for listening.